Recording. All right. All right. So we are recording. What we're going to do today is going to work on some additional instructions. So on Tuesday, we worked on the instruction called LDI, which is load immediate. Okay. The only purpose of LDI is to initialize a register, one of the four registers, A, B, C, or D, with a specific 8-bit constant. That's it. Okay. That's all it does. So the 8-bit constant is not really a part of the opcode, but it is a part of the instruction. So in this case, the instruction consists of the opcode plus one more byte that is the operand that you need to perform the operation. So what we'll do today is, well, a few things. We'll go back to the opcode table. So this way, it is easier for us to see what we are doing today or what instruction I'm demonstrating today. I can demonstrate the store instruction, or I can demonstrate the load instruction. So, you guys can pick one. Do you want me to show you how we write the content of a register to a location that is pointed to by another register? Or do you want to watch me get the content that is pointed to by a register and put and load that content into another register? It's just a direction. Are we Whichever one is harder? They're about the same. I mean, they do. Sorry, say again. Flip a coin. You guys can decide that. Hmm? They're all in the lab. So the LDI instruction is in the lab. The LD instruction, the load instruction is in the lab, and then the store instruction is also in the lab. My recommendation is the store instruction because the other load instruction is somewhat similar to LDI, but the store instruction is doing things in the opposite direction. So I think that might be more interesting. Is that good? Okay, so we'll do the store instruction. So the store instruction is right here. Okay, this is the store instruction, and we're gonna go over the columns one by one so that we can understand what each column is doing in this context. Column A is now specifying 1111 XXYY. Okay, the 1111 part, which is hexadecimal F, is fixed. Okay, so in order to specify a stored instruction, the most significant bits, the four most significant bits, they all need to be one. Okay, there's no wiggle room here. However, the instruction itself is, if you look at the RTL, what it does is you can specify two registers. One register has a placeholder of Y. The other register has a placeholder of X. Now each one can be any one of the four registers A, B, C, or D. Okay. Now somebody's going to ask, I hope somebody is going to think about this and go like, but can they be the same register? Can X and Y be placeholders of the same register? The answer is yes. There are occasions that you might want to do that, which is more common when you're loading than when you're storing, but you can't do it when you're storing. It is less common when you're storing, but it is quite common when you're loading. Yes. Say that one more time. It will overwrite the memory location with a store. Because when you look at the RTL, the left-hand side is not specifying a register, it is specifying what the register is pointing to, and hence the asterisk, which is the dereference operator. So this is why Cisp 360 is a very important prerequisite to this class, because Cisp 360 talks about pointers. Now I know, okay, they usually are in a rush by the time they talk about pointers, but nonetheless, they talk about pointers. So do we understand the RTL? We take the content or the value of whatever register X is representing, and then we store that to the location in RAM memory where register Y or whatever register that Y is representing is pointing to. So the asterisk is actually very important because we have another instruction called CPR, which is copy register. So when you look at copy register, which is Where is it? Right here. So copy register is just x equals y. And there's the load instruction itself is x equals to asterisk y. So whether there's a dereference or not is actually very important. Yes. Can a register is not part of RAM. RAM is a so that's why in this class we have this architecture because we can see okay, quote unquote physically because it's not really physical, but in the diagram you can see the RAM is one component, and then the four registers inside the register bank is a whole different thing. So the four registers are not a part of RAM. Now, are they connected to RAM in some way? The answer is yes. And that's why we can perform operations like this. Take whatever register X has and store that to whatever Y is pointing to in RAM. Is that okay? Do we understand what the instruction is doing? Not so much how it gets it done, which is what I will talk about next, but do we understand what it is doing? All right, very good. So now I want to make an example, right? So I want to create an example so that we can look at an example and see exactly how that works. So what we'll do is I'm taking note of what we want to do, okay? So let's say that we want register, whatever register D is pointing to is going to get whatever register B has, okay? So this is what we want to do. That's the purpose of the instruction I want to demonstrate. So now the question is, what is the opcode? This is RTL, okay? So this line is RTL. The next line is the mnemonic. So the mnemonic is really just looking at column B and substitute Y and X with the respective register. So in this case, what should I use? What is in the parentheses and what is on the right hand side of the comma? Yep, that is correct. So this is the mnemonic to represent exactly the same thing. So given this discussion, I think it is entirely possible to have an assembly language that is just RTL based. Okay. The problem with a completely RTL based assembly language is it doesn't restrict the degrees of freedom enough. Okay, because people who know C would go like, well, can I take whatever B is pointing to and then store that to whatever D is pointing to? Well, syntactically, it's easy to do, but semantically, it is not possible with this processor. There's no pathway that can allow you to do that because at any time you can either be reading from RAM or you can writing to RAM. You cannot be both reading from RAM and writing to RAM at the same time. So that's why, even though RTL is really neat as a representation, it doesn't give us the restriction that we need to kind of confine, what can be specified. Whereas, assembly language or the mnemonic does a slightly better job at that. Yes. It is possible to do loops with multiple instructions. So we will have to talk about the jump instruction and conditional jump instruction in order to implement loops or conditional statements. So we'll get there. Okay, we'll get there probably like within a week after the break. But today we're just going to go over the more basic instructions, which is about moving data around. Okay, we're not computing, we're just moving things around in today's lecture. All right. So the next thing is, what about the binary code? Okay, we know the 1111 is going to be here. So the next question is, what is next? So according to the template of the binary opcode, the next thing we need to do is to specify the 2 bits to specify whatever register X is. X is just a placeholder. So what do you think that should be? So I just need X right now. X is just 0, 1 because in this template, X is the register that is on the right hand side of the equality of the equal sign, and is register B, and register B is represented by 0, 1, and then the other one is register D, which is 1, 1. That is correct. So that means F7 is the hexadecimal of exactly the same bit pattern because 1111 is F, 0111 is 7. So are we doing okay so far? Each row is basically saying the same thing. In the editor, the first line, line 1, okay, is the RTL representation. Line 3 is the mnemonic. Line 5 is the binary opcode. Line 7 is the binary opcode expressed as a base 16 number. Are we good so far? All right. So with that said, we're going to start up the processor because we want to watch how this works. Well, I want to watch how that works. Some of you may not want to do that, but it's going to be what we're doing today. All right. So with this, I'm not even going to bother to use the assembler because we just hand assembled the entire thing. In other words, we converted from the mnemonic to the binary opcode, and then from the binary opcode to the hexadecimal representation. So I can just poke the location where the 7F F7 is supposed to go, and then just type it in. Okay, for simple programs, we can do that. Okay, but for complicated programs, it's not a good idea to do something like this. It's going to take a lot of time for a larger program. All right, so we are technically ready to run the program. Yes, it's F7. I'm fairly sure it is F7. Yep, it is F7. That's okay. All right. So having both register D and register B having a default value of 0 and all locations are also 0 is not really a whole lot of fun. Yes, go ahead. Yeah, we are storing the content or the value of register B to the RAM location that register D is pointing to. Good? Not in this case. Yes, yes, it is. But we are going to change that. Yep, yep. If you really want to know why, it's because I said so. It's not 11. It is 1 1 in base 2. It is different. It is different. Okay. In a test, do you want me to deduct 11 points from your score, or do you want me to deduct 1 1 in base 2 points from your score? 1 1 in base 2 is a better deal. So don't call that 11. 3. Yes. So A is 0, B is 1, C is 2 in base 10, and then D is 3 in base 10. So they're just sequential. Yes. Essentially, whatever Y is the one getting dereferenced. And that's not exactly super hard coded into the microcode, but that's the structure that I prefer to use. Yep. You can see that whenever there are two registers, X is always the most significant, and then Y is always the less significant. It is just a random choice. Yep. because in the binary, but because the YY is referring to a specific output from the register bank, and that output can be used for many purposes. But whenever you want to connect a register to the A port of RAM, it is always that output. So that's the pattern, because you cannot see in one single instruction, but when you look at multiple instructions, then you will see that YY is always specifying which register is going to output zero, excuse me, output one of the register bank. So that's the reason why there's this pattern here. Yep. Oh, okay. Just a thumbs up. Okay. All right. So let's go ahead and check out what this is going to do. But before we do that, as I said, we want to make this a little bit more interesting. So we got to go to a random location and just kind of poke it and change it. So I'm just going to change this location to some random content. We'll have AB here, and then we go to. Okay, so which location are we talking about? The one that is in the red rectangle. Which location are we talking about here? Hmm? Nope, it is not. Because when you look at the register view without going into the detailed edit view, you still use the leftmost column as the address of the leftmost byte of that row. So that means 0C is the address of the leftmost byte of that row. Yes. So if we see this would be 0E. Yep. So now I'm going to document a little bit more. Okay, so let's just say that I want to change whatever is at location 0E to the hexadecimal value of let's say, well, since we have AB, so we're going to change it to BA so that we can spell ABBA in two operations. Is that okay? All right. Okay, so that means I need to do some initialization in the registers, because right now the registers are not initialized. Everybody is just zero. So now the question is, how should I go initialize the registers? All right, so we kind of know the register A is not involved, and neither is C. So which one is register B again? The one on the right-hand side of the equal. Okay, so that one needs to be BA. And register D is the one that is specifying the location that would be overwritten. So that should be 0E. There we go. Thank you. Very good. All right. So I think we are now all set up and ready to go. So I will fast forward through the first two phases of the instruction execution cycle. So I'm referring to the fetch cycle and also the decode cycle, because those two cycles are identical no matter which instruction you're executing. So we are going to fast forward, past the decode so that we can land on the location in the ROM, in the microcode ROM, that specifies exactly how a stored instruction is going to perform its job. Is that okay? All right. Yes, go ahead. Yes. They always have to happen because the instructions or the opcode is stored in RAM. And yeah, you have to go get it and then take a look at it and then figure out, which page of the ROM specifies, how to get the job done. So that's why, fetch and decode are always necessary whenever you execute an instruction. And there are optimization that can be done when it comes to you know these different phases of executing an instruction. There's a special kind of processor called a Harvard architecture. So with those, it is kind of interesting because they allow a lot of pipelining, which means you can be in a different phase of executing multiple instructions at the same time. So things are not exactly just, oh, it's 1, 2, 3, 4, 1, 2, 3, 4. It can be one for one instruction, two for another instruction, three for yet another instruction, and so on. So that makes it possible to execute one instruction per clock. Okay, but this is a much rather much simpler design, so there's no pipelining here. Yes. So this is one core, okay, quote unquote, a core of a processor, but a very simple one at that as well. So when you look at the Intel, i whatever processor, even an i3, or if you look at the AMD, Ryzen processor, one core has multiple ALUs and FPUs already, and this processor only has one single ALU that cannot even do floating point. So it's a very simple design. When you look at a real processor these days, they're far more complicated than something like this. hmm But without showing you this, then it would not be easy for us to really kind of visualize that registers are not a part of RAM and vice versa. Okay. All right. So I'll quickly spell out what the operations are. Okay. The first uh, rising edge is fetch. So this is fetch. And as a result, you can see the instruction register now has the opcode that we specified. And then the falling edge has, there's no particular purpose to the falling edge other than incrementing the microcode pointer. The next rising edge increments the program counter. In other words, the instruction of location 00 has been fetched already. In order to get ready to fetch the next instruction, we need to increment the program counter. So this is just incrementing the program counter. You can consider this as a part of fetch where we post increment the program counter. And then the most important part is the next falling edge, which is the decode. What the decode does is it would use the content of the instruction register to become the most significant two digits of the microcode pointer and then pad it with a zero as the least significant 4-bit of the microcode pointer. So this is the decode. So now that we are done with the decoding, you can see how the ROM is addressing location F70. This particular bit pattern is specific to std in parentheses comma b. Okay, so if you need stc in parentheses comma a, it will be a different location. Is that okay? All right. So I actually wrote a program to generate the content of each of these locations in the ROM because hand doing this is really time consuming and error prone. So I actually wrote programs to generate the ROM content. So if anyone is interested in kind of like modifying this architecture to do something else, I can give you the those programs as well. Cool. All right. So now we need to do the analysis. Okay. So what we're going to do is to look at the three things that we need to analyze. Okay. And I think, oh, no, this is correct. Okay. So we look at the register bank. It is as if we are not using the register bank because you can see the only thing that can either be a dark green or light green other than the clock is a dark green. So that means nothing is enabled in the register bank. In other words, none of the registers is going to change, but it does not mean automatically that the registers are not getting being used. Okay, it simply means none of them is getting updated. We can be reading the registers, but since we are not changing it, we can then move on to something else because we always want to identify what is being changed. Okay, because if nothing is being changed, then we are not looking at something that is useful. Ah, okay, I think we just found something that is going to be active and changed because RAM is selected and it is also being written to. So we are going to write something to RAM. Okay. So now the next question is, what are the next questions? So I always want you guys to think about, okay, given this is what we know already, what are the questions that we want to ask? Yes. Okay, where's the data coming in from? Very good. And so the data coming in is going to change, the content of a location. Yes. who specifies the location to be overwritten in the RAM. Okay, so very good. So both of those are good questions, because at this point the D port is an input. In other words, it is asking, okay, something outside of RAM is like, come on, give me something to update my locations with, okay, or one location with. But the A port is always an input. In other words, it is always asking, hey, tell me which location I should do something with. Whether it's reading or writing, doesn't matter, okay? Because both of those operations require someone outside of RAM to specify which location. Is that okay so far? Okay, so we're gonna have to answer those questions. Let's answer one question at a time. We'll answer the question of who is providing the data, to update the content with. So once we're now going back to that uh, kind of horrendous node which connects to a lot of things. But if you want to see what can be the output of something, there are only a few. Like this one is not an output. This is the input of a register, so we don't have to worry about that. This is an output pin. It cannot specify the content on the wire, so it cannot be it. We see this is an output of a demultiplexer. It may be one of those things, and it is also enabled. So that pretty much locks in and go like, okay, that's it. Okay, this demultiplexer is specifying the content on the wire that is currently being selected. Okay, so then we're gonna look, scroll a little bit to the left-hand side and then look at this demultiplexer. So the first question is, are we even selecting the correct output for this demultiplexer? Because this is output 2, and are we selecting it? Yep, the answer is yes, we are selecting output 2 with this demultiplexer. So this R01DMX or demultiplexer, or the select for that demultiplexer, comes straight out of the ROM. Okay, so these two, they're 2 bits. Okay, let me click on the wire. Oh, it is already clicked. So the selected wire is basically connected to 2 specific bits out of the ROM. And you can even tell which 2 bits, even though it's not really particularly useful to determine that. So we can see that it is bit 9 to 10 out of the split already microcode data. And microcode data is from bit 3 to 23. So it's actually bit 12, I think, out of the ROM that is specifying, the select of that demultiplexer. But the bottom line is it does the 2 bits that we're looking at, the select bits into this demultiplexer, they came from ROM. In other words, it's hard coded in the ROM of what this demultiplexer should be doing. And the same thing with the register output 0 enable. That's also coming out of ROM. Oh, am I looking at the wrong thing? Nope, it's the right thing. So now the question is, now that we know this demultiplexer is indeed connecting whatever is from its input to the output that connects to the data port of RAM, then the next question is, what about this wire? It's coming out of the register bank as a whole, but we know that there are 4 registers inside the register bank. So which one is outputting through out 0? Okay, so now we have to dig into the register bank and see what it is seeing. So we go to view reg bank, and we are basically looking at this particular output. It is coming out of a multiplexer. The multiplexer has a select of 0, 1. So that means input 1 of this multiplexer connects to the output. So we look at this wire, and it's coming out of register B. It is coming out of the Q port, which is the output of register B. Does that seem right to you? Are we using register B to specify the content or the value to overwrite a location in RAM? Okay, this is the right-hand side of the assignment. Okay, so I think that is correct. Okay, so now that that is done, now we go back up and then we try to track down who is specifying the A port. Okay, so now we try to track down this input here. So we look at this input and it is coming out of this multiplexer. This multiplexer does not have an enable, which means it is constantly enabled. The select is dark green, which means it's coming from input 0. So now we track down input 0. Ah, that's an easy one. It is the output 0 of this demultiplexer. This particular demultiplexer also does not have an enable, which means it's constantly enabled. The select is dark green. It is selecting input, is selecting output 0. So now we know whatever is the input here is connected to output 0 for this demultiplexer. So now we know whatever is specifying output 0 in the register bank is connected to the address port of RAM. Is that making, are we making that connection? Okay. So if you think about this and you say, oh, this is awfully tedious, well, yes, it is a little bit on the tedious side. But is it impossible to understand? I wouldn't say it is impossible to understand, because the multiplexers and demultiplexers are nothing more than just switches. Okay. Give me one input and I will connect the input to one of the outputs. Or give me multiple inputs, okay? But I will only connect one of the inputs to the only output that I have. That's multiplexers or demultiplexers, okay? They are only different in the sense of the directions are different. Okay, so now we go into the register bank, we look at output 1, and then we say, okay, this is coming out of a multiplexer. Which input connects to this particular output here? The select is 1, 1. Okay, you can see this is the select. 1, 1 is 3. So input 3 is the input that connects to the output. So we click on this wire, and you can see that it is coming out of register D. So I'm going to pause the explanation of the execution of the instruction, and instead I'm going to ask a question of, does this help you understand what the reference is in C++, in CISP 360? Be- because this is basically what it is, okay? Whatever you're dereferencing is connected to the address port of memory. Whatever the right-hand side, whatever the value of the right-hand side is is basically routed to the data port of RAM, and RAM is just saying, okay, I'm going to override the location, and that's it. Yep. Hmm? Right shift. Yeah, I want to change AB to BA based on the content of register B. So it's going to, so let's see whether it would do the right thing or not, because we are about to have a rising edge. So the rising edge will basically say, okay, whatever the D port is specifying, so let's check out the D port, whether it is actually specifying BA. So let's see, 1011 is a B, 1010 is a A. So it is indeed BA. And register A has E as 0E, and that's pretty clear because 0E is a location that is already highlighted. So we know that is actually what port A is specifying. So indeed, it is a 0, 1110 is a E, so it's 0E over here. All right, so I think we are ready to do another control T. So I'm going to type control T. We're going to have a rising edge, and this location should now change from AB to BA. Control T. There we go. Okay. So are we doing okay so far, in terms of not really just understanding the store instruction itself, but understanding the process of how to track down how components of the processor are routed between each other as we execute an instruction. Because it is not the product, it's not the product that is important, it is the process that is important. So I'll be getting the process. Okay, very good. So my recommendation is to repeat this process. You have to repeat this process to a few other instructions. But right now we only have LDI, LD, and ST. So it would be a good idea to apply this to the LD instruction. Okay, you have to understand what the instruction does, set up the registers so that you expect a certain result from executing that instruction, go through the same process, hand assemble the opcode, stick it into RAM, and then just do the control T step by step and watch the processor decode. And then after the decode, you go in and then you do the same analysis that I just did today, as well as the process that I did on Tuesday, to watch how the components are eventually connected because of the multiplexers and the demultiplexers. That is you have to spend some time to do that. Okay. The first time you do it, it will take a little bit of time. Okay. It might take you 15 minutes, half an hour, or something like that. Okay. And then the second time you do it, you will probably end up using maybe 60% of that time. The third time you do it, you're like, oh, okay, much faster. Okay. So it is something that it's a skill that you can develop. Okay. But you have to put time into it. And this is basically studying for exam two, because exam two will ask you exactly about how instructions get the job done in the processor. Yes, if D is not empty, B. Well, okay, so I'm going to ask you a very annoying question. Define empty. Why do you think 0 is empty? Maybe I'm ready to initialize a variable that is living in RAM to 0. There is no such thing as empty. I know this is not a psychology class. There's no falsy value in assembly language programming. There are just bits, binary digits. That's it. Because we are at a bare metal level. There's no interpretation of what that 0 0 0 0 0 0 0 0 means. It can be specifying 8 pixels on the screen. It can be specifying a value of actual zero. It can be specifying anything. How many what? How many? What do you mean by foot gunning? Okay, how about I answer the question on the flip side? There is no guardrail whatsoever. Welcome to assembly language programming. Yep. No, there's nothing magical about it. When the stars do not align, you debug the program and then you make them align. There's no empty again. There's no empty. It's zero. Yes. It it will do whatever you tell it to do. If you tell it to do the wrong thing and which is contrary to what you want the programs to do, you are at fault, not the processor. Yes. Say again. The register bank? No, the register bank is storing intermediate values that you need for computation. The variables are actually stored in RAM along with the opcode. So there will be, so once we get to the concept of a stack, then we'll see that everything is on the stack, except for very few cases, where we store something as a global variable, but then everything that is not a global variable is on the stack. So we'll get to see that later. Okay, we'll get to see that later. And by that time, I will also recommend you guys, for people who want to get some additional tutoring, those people can use my ChatGPT tutor bot, for that I specifically programmed for this class. And from some feedback from last semester, it is okay. It actually works up to a certain point. I actually had to specifically tell the GPT not to disclose code. It was basically able to look at C code, understand the processor itself, and crank out the equivalent assembly code. But it is not even a compiler. It is just a LLM. It's just a large language model. It's a little freaky, okay? To me, even to me, it is a little freaky. It's like, whoa, it can figure this out. I did not expect it to be able to figure out, how to implement a particular program written in C in assembly for a architecture that even does not exist in the training material that it was exposed to. So anyway, well, that's the age that we are living in. All right, so we just spent what, about 40 minutes to explain this one instruction. So we're gonna go take a look at some programs. Okay, so instead of looking at the micro scale of how a single instruction execute, now we're gonna go back up to a macro scale to just kind of look at what can we do with just these three instructions, because all we have talked about is LDI from Tuesday, ST from today, and then just kind of LD, which is kind of like a combination between LDI and ST, okay? Because it would do the indirection like ST, but instead of storing to RAM, it is reading from RAM. Okay, so that's the only difference between ST and LD. So we're gonna write some programs, okay? And this is the fun part of this class. The fun starts about now. So we'll go ahead and I'm just choosing a terminal. Okay, I think this one is fine. But choose this one. Whoop. All right. And I'll go, to the temp folder and I'm going to write a fairly simple program and I'll explain the concepts along the way. Okay, so this is a simple program, but it does have some concepts that I need to explain. That is in today's lab. Okay, so we'll say memory operation dot ttpasm. So as I mentioned in the previous classes, the extension really does not matter. All you're editing is just a plain text file. So that means in Windows, Notepad will be able to do this. Okay, not a problem. If you're on a Mac, you have to be more careful because on a Mac, there's no dedicated plain text file editor. You do have an editor, but when you save, it is more likely that it's going to save in rich text format or something like that than plain text file. So you have to be very careful when you save. You have to very specifically say, I want a plain text file. So I cannot remember exactly how to do it, but since you guys are the ones owning a Mac, owning a Mac, I think you probably know how to do that. All right. But in this environment, having a TTP ASM is important because it allows syntax highlighting from my perspective. So now I'm going to run, specify a program. So let's just say that I've used LDI register A with something, okay, and that something is uh, three underscores for the time being. And if you want to have comments, I'm borrowing the comment syntax from C++, but just the slash slash. It does not recognize slash asterisk to allow inline commenting. It only has slash slash where you can start comment, but only to the end of that single line. Okay, so you can do that. Okay, so we want to say load the address of blah. Okay, and I'll specify blah later. And then I'll say LDIB with load the uh, new content at blah, okay? And then I'll say STAB, okay, to override blah with the new content. Okay, so now the question is, but exactly where is blah? Okay, now this is, yeah, go ahead. Oh, okay, thank you. So this is supposed to be the content is register B, so this is what it's supposed to be. There we go. Okay. So I'm still not using the LD instruction, which is okay for now. Um, all right. So now the question is, but tech, where is blah? Okay. Well, this is how I can specify the location of blah. Yes. Nope. It's still LDI because the new content is still a constant. Every time you if you know the value that you want to load into a register, you're looking at LDI. If the content is at a location that is pointed to by a pointer or a register, then you're looking at LD. All right, so this is how we get to blah, okay? So blah is a label, okay? This is how you define a label. A label is an identifier followed by a colon. It is the same as how you define a label in C++. Now, you may not have an opportunity to define a label in C++ because the only case you need a label in C++ is when you use the goto statement, which you were probably told not to use. Okay, but later in this class, you will find out that we're going to use labels a lot in this class because that's the only way you can specify a particular place in your program. But for now, we are not concerned about jumping and stuff like that. We just want to specify what blah is. So byte 0 is telling the assembler to go like, okay, reserve a byte here and initialize it to 0. That's what byte 0 is specifying to the assembler. Okay. So right now I am using, let's see, 0, 1, 2, 3, 4, 5. So I'm using 6 bytes in this program. Let me show you how I counted to 6 bytes. Each LDI instruction takes 2 bytes because the first byte is the opcode, the second byte is whatever the immediate value is. So the first line takes up 2 bytes. The second line takes up 2 bytes. ST only takes 1 byte because there's no constant that it needs in order to finish the operation. So that's why ST only takes 1 byte. The byte directive also only takes up 1 byte because every time you use byte, it only reserves 1 byte, but it does allow you to specify the value of that location. So you do not have to make it a 0. If you want to make it like 71, fine, make it 71. Okay, so now I go back and say, okay, I need the address of blah. So the way you do that is simply to specify the label blah. So the label on line 4 is defined to the address at which the assembler is going to put the next thing. Okay, in other words, on line 1, the assembler goes like, oh, okay, I need 2 bytes. The first byte is the LDI opcode. The second byte is going to be whatever the blah resolves to be. Okay, and then on line 2, it's going to take 2 bytes. Okay, because LDI is going to take up 1 byte as an opcode, and then whatever the underscore 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 is going to be the second byte. So it's going to take up byte 0, 1, 2, and 3. Byte 4 is on line 3 because the ST instruction takes up only one single byte. So that means by the time I specify byte 71 or 71, this time is actually 71 because it's in decimal, it is using byte 5 of the entire memory space. But blah as a label is defined to be whatever the next byte is, or whatever is going to be using the following byte. So that's why blah is going to define to merely an integer value of 5. Okay, so I will show you when we get this to the assembler, I will show you exactly how you can check every single one of the things that I just said. But let me address the question first. On which line? On line two? No, nope. There's no dereferencing on line one. Line one just says, whatever label is, put that into register A. The label is defined to be the address of this byte. Yeah, that is correct. There's no dereference. Line one does not do any dereference. It simply says whatever the label is, whatever the value of the label is, copy that to register A. And in this case, the label blah is defined to be 5 because by the time we get to the definition of line 4 of on line 4, the address, the next available address turns out to be 5. We use what? Yes, B is basically a temporary register, just so that we have a place to stash the value that we need to use to overwrite whatever is at the location of blah. Yes. Yeah, you can define the label, but this time you want to define the label slightly different way, slightly differently. So you can say this is yada yada, yada yada. Yeah, then you can define a different label. So now you can define yada yada, yada yada. And but this time you can use a different form of a label definition. Instead of giving it no specific value, which means it is just going to be um, the address that the assembler is at when it's assembling the program. Now we can specify exactly what value you want that label to be defined to be. So there are two ways to define the label. The first way, which is the way on line 4, is just defining the label to be the location of where the assembler is at during the assembly process. And then on line 7, it allows you to define a label to be whatever value, or it can be like an expression, but we'll talk about a postfix expression later. But these are the two different ways of defining a label. Yes. Okay. All right. So the question is, can we do something like this instead without line 2? Okay, like this, right? The answer is okay. So I knew this question is going to come up. And that's also the reason why I made my own processor, because in order to specify the second operand on line 3 to be yada yada, you need to have the pathway in the processor to do something like that, which it does not have. Because if you want to specify an immediate value like yada yada, which can be some arbitrary value, it has to be stored in RAM. So that means you have to grab something in RAM that is usually right after where the opcode is, just like the LDI instruction, and then you want to store that into a location of RAM that is pointed to by register A. You cannot do it in a single instruction in a RISC processor. Now, can you do this in a CISC processor? The answer is yes, you can do it in the CISC processor, because in the CISC processor, there are registers that are not available to the programmer, that are completely internal to the processor, that allows this to be split into like two steps. And then we use the internal unaddressable register to accomplish to accomplish the instruction. But because this processor is a RISC processor, we cannot do that. And I'll explain what a RISC processor is as well. So let me look at the time. Yeah, we got plenty of time. I can explain what is RISC versus CISC. Okay. So I know I'm digressing a little bit here, but I think it's kind of important because of because of how the topic was brought up. So RISC is RISC. It stands for Reduced Instruction Set Computer. The opposite is called CISC, which is Complex Instruction Set Computer. I can give you some examples. The most important example in this case is ARM, because just about everything is ARM based except for Arduinos. Okay, Arduinos, on the other hand, are AVR based, but those are also RISC processors. For some of you, well, I don't think anyone here is going to transfer to Berkeley because this class is not actually transferable to Berkeley, which I talked about a little bit already. So they have another processor architecture, which I cannot remember for now. It is their own architecture, but it's also RISC processor. So CISC processors would be your typical x86 processor, which most people, you know, oh, you mean the AMD 64 instruction set? Yes. So anything that runs the AMD 64 instruction set is a CISC processor. So you go like, what is the difference? Well, the difference is with a RISC processor, each instruction can only do a little bit of operation. Okay, it is as minimal as it can be almost. With a CISC processor, each instruction can do a lot of things. Okay, it can do this, combined with this, and then do this. Okay, so we can kind of imagine that. Oh, so that sounds like a CISC processor is more efficient because with one single opcode, now I can have a bazillion operations specified. I could have turned TTP into a CISC processor because I have allocated 16 locations in the ROM for every opcode. So I could have go like, oh, first do this, and then do this, and then do this, and then do this, and then do this. But instead, I just go like, just do this. We're done with this instruction. But we are not done yet. I still need to do, well, use another instruction to specify what else you need to do. Yes. Yeah. Yeah. But the focus now is, but why do we have these two, and which one is quote unquote better? Okay, the um, what is better? There's no such thing as better or worse. Okay, those are judgment words and used to describe things that are usually not technical. But when it's technical, usually it boils down to does it work or does it not work? Okay, or are we optimizing for a particular number? Okay, so as it turns out, in data centers, okay, the one thing that restricts how much processing power you can pack into a single data center as a structure, as a building, is heat extraction. How much heat can you extract out of a certain amount of space, give per second, per minute, whatever unit you want to use. Okay, turns out that is the limit. And given that is the limit, the interesting thing is risk beats CISC. You go like, that's not that possible. But that's not possible. A single instruction can do more things, and how can that be more energy, less energy efficient? Because because overall per amount of work, CISC is less energy efficient. The reason has to do with this. With a CISC processor, it takes more silicon on the die. Okay, and at any point only a smaller portion of the silicon is actually working. The rest is just going like, we're just humming along, we're not really doing anything important, but they're still gonna getting clocked, they're still getting, they're still consuming power. Maybe it's less, but they're still consuming power. So that's why with a CISC processor, it is actually less energy efficient compared to RISC processors. So IBM has switched to a RISC processor architecture a long time ago for their mainframe computers, or quote unquote mainframe computers. They prefer to use the term enterprise computing these days instead of mainframe, because when people think of mainframe, they think of black and white pictures of hairstyles from the 60s. So the IBM prefer people to think of enterprise computing. Yes. Sorry? It is Human brains are not even silicon based, so I cannot tell you what it is. It does not belong to either of these groups. So given that is the case, so I use RISC as an architecture to explain things, because in a CISC architecture, you can just do a function. When you call a function, we're not quite there yet, but when you do a function call, it's one instruction. when you return from a function, it's one instruction. It does not tell you under the hood how the stack is being utilized when you're calling and when you're returning. The same thing, for many other things, it doesn't demonstrate what is under the hood, and I want to explain things that are under the hood as much as I can. So that's why that's why TTP is kind of as risk as it can possibly get. It's not quite that pure risk because I found out that if I make it that pure, I cannot really have meaningful programs implemented. So I kind of have to make a trade-off and go like, yeah, we kind of have to sacrifice a little bit of the pureness of risk in order for it to be at least practical enough to implement the Tower of Hanoi recursive algorithm. Yes, we can actually do that. With this little processor and 256 bytes of RAM, we can implement the Tower of Hanoi solution. Do you guys know what is the Tower of Hanoi? No? Okay, look it up. Okay, I'll just type it on the screen so that you know what this is, and but I'll leave it up to you guys to look it up. It is called the Tower. Oh, not Power. The Tower of Hanoi. Yeah, so look it up. Okay, it's what? Yeah, but in assembly it's a little bit more. Anyway, so that's our discussion of risk versus Cisp, which is actually part of the student learning outcome of this class. So there you go. Okay, you just learned it. Yep, go ahead. hmm The location. No, it is going to put it into a memory location that is after the instruction of ST. So I'll show you, okay? Because when we look at the assembler view, it will show you exactly how memory maps to the program code itself. The instruction, when it executes, would put something into register A, but when the program is just being assembled, then nothing is happening to register A. Because putting something into register A is a runtime behavior. This is just statically describing what opcode and constants should be in RAM so that when we run the program, the instructions, the opcode, when they execute, will end up putting the correct value into register A, into register B, and then whatever register A is pointing to is going to get whatever is at the location that has the constant of 71. Yep. No, there's no garbage collection. Okay, the best way to describe this is it will do whatever you tell it to do, and this is exactly what we tell it to do, and that's exactly what it's going to do. After line 3, what is the value of B? It will still have what we know as 17 as a decimal number, or it's going to have 1 1 as a hexadecimal number, or you can also see it as 00010001 as a binary number. That is correct. It is nope, 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 nope. Okay, but the whole yeah, but the whole discussion, started the whole discussion of risk versus CISC started when you asked, can we substitute B on line 3 with yada yada? And the answer is no. It is not a syntactic limitation. It is a limitation because of the processor itself. Okay, and that part, that message is really hard to convey if I were to teach this class using the x86 architecture and to go like, oh, this is the syntax, okay, of the instruction set, and we'll just kind of be writing programs using the instruction set because everything becomes just syntactic in that case. We are not understanding the actual architecture limitation behind the syntax. So that's the main reason why I want to design my own architecture to teach this class is to demonstrate, oh, the assembly code is merely a tool to help you put the opcodes together without having to remember all the zeros and ones and driving you crazy. Yep, you just do LDI B0 somewhere, whatever you need that to be. Each instruction does exactly what you tell it to do, no more and no less. And the whole point of this is you can actually see every instruction run clock by clock and see how it runs because you can see the connection or the connectivity between the components. And that's going to be the focus of exam 2 is to see whether you understand this particular aspect of the processor, which basically means today's lecture is actually really, really important. So for all the people who are texting and not taking notes or not paying attention, you might need to rewatch the video because otherwise exam 2 is gonna suck like big time. All right, so let's go ahead and run this program. Okay. All right, so we're gonna go back here, go to the source, get rid of everything in column A. So the way I do this is I select the column and then I press the delete key and that clears the content without changing the equation stuff that is needed. Then I click on the first cell, not double click. I don't want to see the blinky cursor. Then I type Control V because the other program is already in the clipboard. And this will paste the program in without altering things that you're not supposed to alter. Okay. So because I want to demonstrate this because I observed a few people having a problem and I just want to make sure that we understand this process so that we don't run into those problems. So we go to the assemble view. Okay, so this is the what I talked about a little bit earlier. You can see that column A is the actual mnemonic, and then column W, X, Y are now super duper important. I cannot use the mouse pointer because I have comments, on these cells, and whenever I put my mouse pointer over, it would show the comment instead. So I'm gonna have to point to it by hand. So LDA blah is at location 00. 6C corresponds to LDIA. The 6, which is blah, is now in column Y. In other words, the mnemonic of LDIA blah assembles to the 2 bytes, which is 6C06, and these 2 bytes are at the location starting at address 00. Yes, yes. Well, it's a little bit of scripting here. So the way it resolves that is it allows forward reference, which means the reference is before the definition. Um, and the way it does that is in the JavaScript code, so you can hmm, hoisting. I cannot remember exactly how that mechanism was implemented, but if you look at the JavaScript code, it does that. And on top of that, whatever you specify after the comma doesn't have to be a label. It can be a full expression that involves one or more labels. So it parses the all those expressions and it will figure out which part of it is still unknown, and then it will just go like, okay, I'm gonna wait until the label is defined. Then basically it figures out the dependency, between the references and the definitions. So you can have a whole chain of label definitions where one label's definition depends on on some other labels. And as long as those dependencies are not circular and they end somewhere as a constant, it will still be able to resolve it. And that code is in the JavaScript code. So if you go to, I guess, extensions and go to the actual scripts of this particular spreadsheet, you can see that. All right. So you can also see, on line 6, how byte 71 is just saying, oh, okay, we're going to put 47, which is the hexadecimal representation of 71. We'll just use location 06 to store that 1 byte that has a value of 47 in hexadecimal, which is 71 in decimal. Is that okay? So does this help to demystify, some of the questions that we saw earlier? Okay, cool. All right. So now we're gonna, we will go to the RAM file because this is also part of the whole process. Is you have to go to the RAM file tab to go to File in order to download the CSV file. This is how we get the content of the processor into the RAM of the processor. So now we specify this as memop, okay? I just prefer to use the same name as the source file. This way, I don't get confused myself. So now we go back to Logisim, and then we go to, oh, Control R first, okay? Because this time we use Control R because we do need to clear memory. Right click, load image, and then specify the location where I stashed memop.csv this time, comma, separate the value. And now we have the content here. So with this program, I'm not going to single clock like using Control T to kind of do the whole thing. So I'm just going to make it real quick. So now the question is, but how do we know the program is all done? Okay, one way you can determine is the program counter is not moving anymore. And when did you learn that trick? On Tuesday, exactly. Except some people did not read the instructions and they never learned that trick. So you have to read the instructions of the lab. Okay, the lab contains instructions that are actually useful past the lab itself. Okay, so then there are persistent knowledge that you need to retain from doing the lab. But there's another sign, if this halt flag is a 1, that also, signifies the program has reached a halt instruction, which means at that point you can also stop the simulation and start to look at the actual result of the simulation. So we're going to do this. Okay, we're going to enable click. And unless you really want to see the animation of the instructions executing, you can always bump up the tick frequency to as high as it can get, which is 4.1 kilohertz. And then you can do a control K instead of a control T, because control K enables tick, which means the clock pin can now toggle by itself. And that is the main reason why the clock pin is not the same as a normal input pin, because a normal input pin needs you to be doing all the clicking, right, to alternate between the 0 and the 1, but the clock pin is can be automated. Okay, so this is what we'll do, Control K, and now the halt pin is a 1, and we want to find out what the program has just done. But that would not be a good idea, because the best idea is to figure out what the program should have done first, then we go check whether the program has done that or not. So we know that we're supposed to overwrite the location of blah with 17 in decimal. So that means we're expecting the content of 11 at location 06. Okay, so we have to have an expectation of what the program is supposed to have done before we check what it did. So now we go back here. We can now go to RAM and we go to location 06. This is 04, 05, 06 is indeed a 1-1, which is because 1-1 is in hexadecimal, it means it has 116 and a 1. Well, when you add up those two, we get 17. So are there any questions about this? So I know somebody is now thinking, okay, if this is what it takes to run a program every freaking single time, This is a nightmare. Okay. Well, you're not incorrect. Okay. It is a lot of steps, but I have written scripts to make this a lot faster. So I'm hoping what I'm going to demonstrate next is going to help you guys, help convince more of you to use the script instead of hand doing everything. You can still hand do everything if you prefer, but I have ways to kind of make it a little bit more convenient. Yes, please. And why would it be a F2? No, F2 would be 15 times 16 plus 2. You're forgetting how to interpret numbers. Every digit specifies a quantity of a power of the base based on the position of the digit. That's important, okay? Because that's how we read numbers. Whatever base does not matter. That's how we read a number. Okay, so let's go ahead and do it in the more convenient way. Now, before you do it in the more convenient way, because of a bug that I still have not fixed yet in Logisim, I did not write Logisim, by the way. I inherited Logisim from somebody else. You always have to start the program with a no op, which is no operation. I don't know exactly why, but I haven't got the time to debug it yet. But that's just the way it is. Okay, you have to start a program with no op. But once you have done that, now I can switch to a folder that has a really cool, well, I wouldn't say really cool, but a useful script, okay? Useful script. It's called River Spider, okay? And don't ask me why it's called River Spider. As a child, I was, actually really deathly afraid of spiders, but not anymore. Okay, so, hmm? I do not have a spider pet, but I do watch YouTube videos where other people have, spider pets. Yep, go ahead. Um, well, that's an interesting question. It's because of jumping spiders because they're different from most spiders. Yeah, they're not big either, but they're kind of cute. Yep. Yeah, they are. All right. So this is how we can do it. Okay. So this is going to be like you go like, wow, this is like kind of cool because with this script, you just press the enter key and it will do everything that I just did by hand for you. And it has and there's a little bit of a bonus too. Okay. So the bonus is it will actually trace the program as well, and it will upload the trace back to the spreadsheet to analyze the trace so that you can very easily figure out how the program ran and what happened when it ran. Okay, I think this is one of the most useful tool for learning assembly language programming because now if I go back to the spreadsheet, oh by the way, I should have closed that first. It's okay, it's not a problem per se, but I should have done that. So now if you go to the analysis tab, now it reflects the execution of the program. I normally do not talk about this tool until quite a bit later in the semester, but I think this is not bad. Okay, just talking about this a little bit earlier. You can see column A tells you where the program counter is. So you're looking at you can look at let me see what how shall I put that. The rows are kind of like frames in the film, and time travels in the order of the cell numbers. Okay, so row 2 is saying when we execute the no op instruction on line 1, nothing happens. RAM is not being read, nor it is being written to. None of the registers changed. None of the flags changed. And well, I guess that really fits the description of no op, which is no operation. Okay, row 3 of the trace says this is the instruction on at location 01. At location 01, it corresponds to line 2 of the source code. It is our LDI instruction. And the result of executing that instruction is register A gets a value of 07. Okay, and so on. So we get to, let's say we get to line 4 because I know you guys are wanting to go to the lab. So on line 4, it is a ST instruction. So right here, we can see that memory is written to. Location 7 is now updated to 11 in hexadecimal. But we can also see how the registers themselves got updated along the way. So this is um, I think this is a really good tool to understand, as a program, as when you have multiple instructions, how the instructions interact with each other, how the registers got updated, how RAM is updated, and how the flag registers are updated. Now, this program does not touch the flag register at all, so it's not reflected here. But this is a good tool, and I will teach you guys how to install that in different operating systems, when we come back from the break. So we still need to know today's lab, the access code of today's lab. So today's lab is here. Let it expose. And the access code is just lowercase LDI. I'll see you all at the lab.